This expression gives us an approximation of any polynomial f of x. Let's apply it to the cosine. Then our first derivative, f prime of x, is going to be equal to the sine of x, actually the negative of the sine of x. And our second derivative is going to be the cosine, negative cosine of x. Our third derivative is going to be equal to just the regular sine of x. So as a result of that, our fourth derivative will be equal to f of x. Fifth derivative will be equal to f prime of x, and so forth. But in order to get the coefficients, or the c sub n's, we need to figure out what f sub n of a is. In this case, we want a to be equal to 0. We want to replace all of these x's with 0 and state what those values will be. Well, f of 0 is the cosine of 0, which is 1. Then the sine of 0 is 0. The cosine of 0, negative of the cosine of 0, is negative 1. And the sine of 0 is going to be 0. So, the Taylor series for the cosine alternates between 1 and negative 1, and every other term is missing. The cosine of x is going to be equal to 1 over 0 factorial, that's the c sub n, times x minus 0, because a is 0, to the 0 power, so x to the 0, plus 0 over 1 factorial times x to the 1, plus 0 over 3 factorial times x to the 3rd, plus 1 again over 4 factorial times x to the 4th, plus 0 over 5 factorial times x to the 5th, plus, and on and on and on. Now we can rewrite this in a more simple form. Ends up being 1. It's going to be minus x squared over 2 factorial, then plus x to the 4th over 4 factorial, x to the 8th over 8 factorial, and minus on and on and on. There's the power series for cosine. Now we'll find the power series for sine. Okay, there's our formula. We start by figuring out the derivatives for sine. And the derivative, f prime of x, is equal to the cosine of x. And we can see already that it's going to repeat like the cosine. So the second derivative is going to be negative sine of x. Third derivative is going to be the negative cosine. And the fourth derivative, the derivative of the negative cosine, takes us back to the sine again. So our fourth derivative is equal to our third, to repeat. And we keep cycling along like that. Well, now we need to know what the values of these are at 0. So let's just put 0 in. Okay, plugging in 0, we have the sine of 0 is 0. The sine of cosine, the cosine of 0 is 1. The sine of negative sine of 0 is 0, and negative cosine of 0 is negative 1. So just like the cosine, every other term vanishes, but starting with the first term vanishing. Then, every other term has an opposite sign. The sine of x is going to be equal to 0 over 0 factorial times x to the 0 over 4 factorial, and so on. So then our sine of x, writing it without the terms that get canceled out, is equal to, well, the first term that we get is x, so it's x minus, and so on into infinity. So the sine has the odd powers of x, and the cosine has the even powers of x. Let's look at them side by side. Okay, there's our sine x, there's our cosine x, and we know now that e to the x is equal to 1 plus x plus and so forth. So looking at these power series, we have 1 x squared over 2 factorial, x to the 5th over 5 factorial. It seems that between sine and cosine, we have everything we need to make e to the x. So if this is e to the x, then e to the ix power is going to be equal to 1 plus over 6 factorial and so on. Now what happens with the powers of I? Well, I to the 0 is equal to 1. I to the 1 is equal to I squared is equal to negative 1, and I to the 3rd power is equal to negative I. I to the 4th power, well, negative I times I is going to bring us right back to 1 again. So let's apply this to the series for e to the x. We get 1 plus ix plus negative x squared over 2 factorial, 5th over 5 factorial, and so on. This is 1 minus x squared over 2 factorial plus x and so on. Looking at the series for e, we have minus x squared over 2 factorial. And if we had continued it, our next term would be minus x to the 6th over 6 factorial, and so on. So every other term is a term from cosine x. Now sine of x, factorial, and so on. And if we look at this series, we see that we have all of the terms for sine, but each one is multiplied by I. Therefore, cosine x plus I sine x is equal to e to the ix. Now that is a very powerful identity right there. As you know, the sine and the cosine are defined by the unit circle. The sine is this coordinate, and the cosine is the horizontal coordinate. If we think of what we normally think of as the y-axis as the I-axis, and we think of what we normally think of as the x-axis as the real number axis, if we take the angle theta to be x, this complex number allows us to represent the coordinate here. So this coordinate would be a complex number a plus bi, where a is equal to the cosine of theta and b is equal to the sine of theta. Well, a plus bi is equal to e to the ix, so we can also write this coordinate as e to the I theta. All right, let's prove the identity. Proof. Let x be equal to pi in this equation. If x is equal to pi, then we have the cosine of pi plus the sine of pi, I times the sine of pi, is equal to e to the pi I. Well, the cosine of pi is negative 1. The sine of pi is 0. Therefore, negative 1 is e to the pi I. We've completed the journey. Thank you for coming with me.